Hey, so welcome to the last practicum of the semester. This is the practicum based on like adversarial attacks that we were supposed to do, and technically had 2 days after the lectures, but it was also not too much, I think, to do because the dashed portion of the ellipses were not too much. But yeah, let's see. We'll go through it and then probably it makes more sense. It was similar to previous practicum, so you have to just fill out the places where it's like given blanks for you or to do comments. Uh, we have to start by some kind of like standard libraries. We are going to show some plotting, so we will also import plotting libraries from Matplotlib, for example. Progress bar, I don't think this requires too much of descriptions here, but yeah, basically these are all needed for the rest of the project to be done. You set a dataset path and the checkpoint path. Basically, you have a pre-trained model that you're going to load. Set a seed so that you can get the same results every time you run. And of course, specify the devices, if GPU, if not, then CPU. Here in the second block, what you was needed to do is basically now you have to include both the data set and so there is a task where you have to work with some kind of patches which we actually use later on. So you just specify the path of them here from the GitHub where it is actually uploaded. And if the paths are not there, then you make them. Yeah, it's something reading. Okay, no. So and then if it doesn't exist, or if it's already exists, then yeah, you just can use them. If not, you have to download it. So basically, this is the code. This is also very simple. So this is where your the task part actually starts. What we are going to the topic of the task is basically deep CNN on ImageNet. So what we are going to do here is we use a CNN net architecture, which is ResNet 34. And this is also trained on ImageNet dataset. And we basically first load the pre-trained weights. And then we don't want to train it. So we now want to actually evaluate it. So how it works on some data. And so we actually make it false. So required grad is equal to false. And what we start by doing here is basically now the model is trained on ImageNet, and this ImageNet has a pre-processed so kind of images, and we would so for our task we have to also now you have to have adversarial images, right? So we have to now transform these images to this pre-processed structure of the images data. So we take this mean and standard deviation of this from the ImageNet, and we have a function here defined where we want to transform basically when we will create our adversarial images. So we will transform it based on the mean and standard deviation of this ImageNets. We load a data set which is tiny ImageNet. It is basically a subset of ImageNet, which consists of 1,000 labels and 5 instances for each of this label. Yeah, and then here you transform these instances of the data set. And then basically you make you form batches and all so that we can continue using that for the rest of the training or inference, whatever you want. And what we do here is we also have a JSON file previously, which actually maps these labels to, because we had 1,000 labels, so this maps to index or integer number for so an index from 0 to 999. And we have a JSON file for it. We load it here. Yeah, and we basically return the index. We will see how we can actually go ahead and use this, why these informations are required. But yeah, some kind of, let's say, to structure the project or work, we have to now first define these. And we also define a model where a function where we want to, but with using which we want to actually evaluate our model. So this is an eval model function. And what we want to do here, we want to see how the model is predicting the label. So basically, is it at all giving us like the first preference or something, like with the highest score or something? I mean, the model gives a probability distribution of all the labels. So we want to see if the highest probable is the label or not, or at least if it's present in the top 5. And so what we do is basically take the image. So we go over the image of the labels. We have to move it to the device, the same device. And then so for now we don't have, because we want to evaluate the working of the pre-trained model on the images, so how it does actually in the pre-trained form, so that we can see, then later on probably we can better understand how worse or how good is it doing. And so for now we don't have any noise or something, and we just simply give the image to the model and we have a prediction. And we just increment the TP if it's like, if the label is equal to the prediction, like the top prediction. And if it's not, at least if it's within 5, the topmost 5 labels, then it's like, but we increment the TP5. And now we find the accuracy by dividing by the number of instances. We have the counter for that. And we find a percentage of error by basically simple percentage. And then if you see that this is the score. So here is the scores of the model performing, how it's performing on the data set. And we can see that, okay, around 19%, 9.5%, it is kind of not predicting the correct label. But with 5 in the top 5, at least the label is present for most of the predictions. So it's quite good, I would say. But that's not the point. So we know now how the base model is, the pre-trained model is doing. Now what we want to do here is basically we show for visualization purposes, we kind of plot our labels and like the model predictions and the actual prediction. So here for that, you firstly have to, so when you have the image, you have to now, from the tensor, you have to transform it to the NumPy. Similarly, you have to also map it to the normalization of the ImageNet images and then clip it. And we also talked about clip in the lecture. So it is basically so that the range of each pixel values, it doesn't go under 0 or exceed 1. So it's somehow to be between these values. And yeah, we have the label, of course. So now this part basically only, of course, you will go to the condition where image is none, because we are, the noise is none, because we don't have the noise now. So we just, we have this images with its label. So we just visualize them here or plot them here. If the adversarial image is not none, so this part we would not require now, we'll comment later if we require. And then here what is happening is basically we go over all the predictions and we find the softmax, of course, of all the classes, the probability of what the model predicts. And then we take the top k of the prediction. So basically k is said to be 5. That means 5 classes, and how the model actually predicts these 5 classes. I mean, what's the probability distributions of the top 5 classes? And basically here is basically if the label and the prediction is same, then it's one color, it's C2, so this is green, and if it's not, then it is blue. And then you kind of have these all text titles and X labels. Basically, you can see what means what. So confidence is basically with how much confidence or how much sure is the model in predicting this class. And you can see that the model is clearly okay. And we go over basically every 5 steps till 17. So we have kind of four images here. And we see that the labels, so the model is actually very good at predicting the actual class of the image. And it's kind of with very high confidence, it's saying, so almost the rest of them are 0. And yeah, given only this one, but it's still high prediction, I would say, confidence that it predicts that this is to be tiger shark. So now what we want to do, so we see that how this pre-trained model is doing on the tiny image data set. Now what we want to do is do white box adversarial attacks. And if you recall from the lecture again, so one of the strategies is to follow the fast gradient sign method. And this is how you actually can create the adversarial image. So let's say you're creating X dash or something, which is represented as the adversarial image. We just have to add the gradient of the loss with respect to the original image, and we multiply with a very small value, which is epsilon. And and then we add this to the original image. So this is basically now the gradient part. And what we do is normally what we do is we want to minimize the loss, but here what we do is we maximize the loss. So the reason is because this is unsigned, so untargeted. So that means you don't have a target. You have to move away from the original label. So how we can do that? So here is the first thing that I think these all parts I tried to make it a bit clear so that for me, so that I know which parts are was actually given for you to do. Clearly visible basically. So what you have to do, you are given the model, the images, the label, and the epsilon value. And here's an instruction already given to you. Basically, they want you to clone the image so that you don't have this problem of losing the original image. You just clone them and then make it require gradient because we have to learn the adversarial image, right? So you have to change the tensor. And this is what is your image now. And then prediction, you give the image to the model and then you get the predictions. Of course, you have predictions over all the classes, so you get a softmax probability. You do softmax on the predictions. You calculate the NNL loss, where you give the predictions and the labels, and you get the loss. And of course, you will backward it. And then what you need to do is you update the image now. And it is basically this formula, this function that is given to you. You calculate the noise grad. You can do it also in one line, but basically it's easier to understand this way. So you just have to have the grads of image.grad, and then you just add it with epsilon. Add it with after you multiply with the epsilon. And the reason for using epsilon is basically because you don't want to do bigger updates. So you want to still keep the image very similar to the original one and you want to do little update, minimize the update. And now we have noise. So what we do here basically now in the show prediction function, now because we have the noise is not none, we can go here. So everything else remains as it is. Of course, you will go here, I guess, to the else condition. And here you will have now 2 other images, which is the adversarial image and the noise that you want to also visualize. But the statements are basically same as what you do for the original image. So basically, you just change into numpy, and then you have to normalize it, and then clip it, and then basically show and do the thing for the both of the images. And now, if you visualize them, basically we visualize the same images, and you see these are the predictions on the right-hand side. So the model is now very confident about this is not no longer trench, but it is ELF. So neither of them. So this is no goldfish is also nowhere in this top 5. Great white shark is very minimal here, and this is also there is no tiger shark within the first 5 of the predictions. There was also a question given to you regarding this. Did we succeed on fooling the network on these examples? Okay, despite of minor amount of noise, we are able to fool the network on most of our examples, and you can see that, of course. If you want to not visualize, you have to scores over all the data, test, like the whole day's data set. Then you can also have a similar score of how much error is it making. Now you see that it's kind of like 93%, which was previously 19. No longer it does as good as it was predicting the actual label, which is what we want with so much minimal noise addition. And then over 5, in the first 5, the label is present is basically a bit more times, but it's still quite bad. So how is the performance compared to the error rate of 4.3 on the clean images? Do you have any comments on the wrongly output labeled on the examples? As expected, the model is fooled on almost every images, at least for the top 1 error, top 1 error, and more than half don't have the true labels in the top 5, which is 60%, which is more than half. This is quite significant difference compared to the error rate of 4.3% on the clean images. However, note that the predictions remain semantically similar. For instance, in the image we visualize above, the trench is still recognized as other fish, as well as great white shark being dugong. I have no idea what this is, but yeah, it's a fish probably. So basically they are still in the area of fishes. So where there is fish, they kind of predict a different fish. So this was the first task. And then we had the second one, which is the adversarial patches. And this task was also, a bit different. I think we didn't kind of look into this in the lecture. I don't know if there was an example, but anyway, the task was instead of now, because in the previous one, what we did was we changed each of the pixel. And now what we do is we changed we add a patch over a patch of a different image, let's say, a noise kind of thing again, but we add it over the original image. So only small part of the image is covered by this new patch. And we train this patch by calculating gradient for the inputs, and we update the adversarial input corresponding. So basically what we do is now only train this patch to be a specific target. So each of this patch is trained to have one label. And we basically see that when we add this patch and then when we actually evaluate the model, then the model kind of classifies the patch classes, no longer the original image class. We will start by defining few functions here, which will make sense later on. But first we do is the place patch. Place patch is basically just putting the patch on this image, and we have to find a location for that. So we do a random offsets, height offset and weight offset, width offset, and then we kind of random put this patch there. And before we put the patch, so we have to also map the image now to the ImageNet image. So it's kind of also similar. You use the tanh function to reduce. So basically the patch itself is a very high range. So we have -infinity to infinity, which is not possible for, so we have to now scale down. We have to kind of now put, yes?
But wouldn't it make more sense to use the same seed for the hedge? where to put it on the image.
So what do you mean by seed here? We are still
Like
not training.
I mean, we draw a random number and then use that for the offset. But we could make use the same random.
No, so basically the thing is like the idea is like it doesn't matter where you put the patch on the image as long as it's over the image somewhere, and we only don't do it like only one position. We kind of do it like also like average it like on different places. So to see that it's not it's a kind of
wouldn't make more sense for the evaluation part then? Maybe some areas might be easier to detectable for the.
Yeah, so that's why we're saying that we're not doing only one place, because it can be like in some images where the important part is probably on the left hand side corner and some on the right hand side corner. Then you can, if you have a random places to put the patch, then hopefully, I'm not saying that it's 100% all the time, but hopefully sometime, at least once or something, that it's actually on the image, like the part that is more important. So yeah, I mean, probably you can try to do that as well, and it would be the same, or scores might a bit different, but I guess the idea is to make it much more stable. But let's see. Yeah. Yeah. So now, yeah, we know. So we scale down by using tanh. So tanh has this -1 to 1 score, so it scales down to that, and then we kind of +1, so 0 to 2. Then you actually +1 on those. And then if you do multiply the mean and divide by standard deviation, then you kind of have the normalization value similar to the ImageNet. And then you place basically the image on the original image. Likewise, we also define an evaluation patch function where we do is what is also similar. But what I told right now that we only now don't calculate it once, but we just iterate like 4 different places, and we want to make sure that the model is kind of like giving a stable answer or something. So for stable places, we kind of randomly choose 4 positions where we put the batch. And the rest of the things are similar to the previous evaluation function. So we still have the top 1 and top 5, and we just increment them, and then we have the accuracy for both the cases. Then this was one function that we required it later. We will talk about it when we see. And then what we have here, so we have now, again, this is the part where we start looking into the training loop. What we do here is like we start with a patch with this size. So 3 into k, k we replace with some numbers, and then basically only train this part of this image, and then only the patch, and the training is basically to make it classify to the target label now, so which is specified as well. And what you are required, so what you do first is you split the train and the data set into train and eval. Of course, you have the data loader, and here is the part where you actually initialize it with torts.zeros, and you have the dimensions here, which is patch size is given 64, let's say for now. If it's nothing is specified when you're calling, then it's 65, 64, and then you make it required guide because you want to train this, right? And then, yeah, basically you have to optimize and loss model, and now the training loop. And for that, these are very similar things again, so it's what's required. And now what we do is like we have to now have the new labels, right? Like target the patch labels as the target labels. So we just make the same dimension vector as the batch size with zeros, and we just fill it with the late target labels. Then we calculate the loss. So given the prediction and the labels. Of course, we send the image to gives a matter to have the predictions. Otherwise, how will you get the predictions? So I think I can miss it. And then you back propagate. After you do this, you will call the eval patch, and you see that from here we already return this scores. Why I'll tell you, but let's say that we return the scores for now. And now let's move towards the next one, which is basically loading this some kind of JSON which has the scores, let's say. So what we are doing is basically we have the scores and we are keeping it in a file. So we are storing it so that we don't need to run it right now, because what the function now I showed you is basically for one kind of instances, one patch. But what we want to do is like for multiple patches, and also for we want to also change the number of pixels. So basically, not the pixel size, basically. So that's why it would take a bit of time. So let's say that for now we stored it. But in case you want to train it with a different kind of patches, you can also call it then you will have to kind of make some adjustments here. But we go there and then we talk about it. Yeah. So it's basically the function here. There's no function here. So basically you just load the results. But in case you want to save it, if you want to change, if you want to have more patches or more, to train your model, then basically you have to then save the results, and then easily, you can also directly call it the visualization from them, but it's easier if you do minimal alterations, and then you can save the results and use it later on. We'll come to that. Why would you need to save and why do you need this results? But let's say, you have to do that if you need more patches to train. This is the get patch function, and this is basically where you have. So what you have is like I told you that for each of the class that you are creating this. Let's go here, it's easier. So you have this 5 classes that you take, this toaster, goldfish, school bus, and then you have this pixel sizes for each. So you want to create patches for each of this class and for each of these patch sizes. So this is what you are going to here go. So you want to get patches for these classes and these kind of sizes. So you go over the classes, you go over the sizes, and then, this is basically, if you don't have, you load the tensor from the path, but if you don't have it, you then have to call the patch attack here. So this is where you first call the patch attack. And then if you go here, while training, you call the patch place patch because you want to train the model on the adversarial image. And then, of course, placing patch requires page forward. That's why it's needed. And then here, after you backpropagate and you've run all the epochs, you now evaluate these patches with the model patch and the test sets. And the classes. And basically here you get the scores. So now after you get the scores, what you do here is basically how you form the results. So you form a dictionary, but we actually also have the results. Result is similar to this. So basically for given class and given size, this is like the top one, and this is like the top, if the label is present, the top 5 classes. Then, and also you have the results, and basically you also have the patch there. Now, why do we need this? So we will actually need to visualize. I think it's easier to store instead of running every time, so it's easy now. So basically we visualize this patches firsthand. What we do is on the rows we have the sizes of, so this 32 and this is 48 and 64, that the 3 sizes that we considered. And on the columns, we have the different classes, yeah? And basically what we do is we visualize how this patches looks like in each of these sizes. And there is actually a question for you here. I think comment on the difference between patches of different classes and sizes. Example, do you see any clear patterns in the patches? I guess if you look in the patches, it's kind of seems to be a bit more realistic from the smaller ones and then the 64th ones. But the descriptions is also what they say. So we can see clear differences between patches of different classes and sizes. In the smallest size, which is 32 into 32 pixel, some of the patches clearly resemble their classes. For instance, the goldfish patch clearly shows a goldfish. The eye and the color are very characteristics of the class. Yeah, it kind of looks like a fish, right? I would say this looks a bit more, but yeah, this is more than this at least. Yeah, this is kind of also the pineapple looks a bit more like a pineapple, I think. I mean, okay. And then yeah, the larger the patch becomes, the more straight the pattern becomes. So for the goldfish, we can still spot some regions that might represent eyes and characteristics, orange colors. But yeah, the idea is to look into this to see that how you can recognize these classes, because the idea is like even by looking at this for humans, it should not be that different. But that's the thing. So how good is which one? So in general, the idea is like they say that it says that it's, I mean, also you can see that it's a bit more towards, I mean, the 32 feels a bit more realistic than the 64 one. And, but yeah, they also say that nevertheless, we can easily spot the alignment of the patch of the class, even on the larger scale. So basically, I think this goldfish still is kind of an orangey thing, and then here the school bus, which is in general I think yellowish. I don't know if it's for sure, but in from my region it is anyway. And pineapples are kind of green, so this is also something you can see. Let's move forward. This is only the increase the font size. So this is now what we are doing is visualizing, not visualizing, we have to now displaying how the model works on the whole in the test data set. And we show it for the first time on the top one and for 3 of these patches. And you can see that when the patch size is 32 into 32, the model is okay, it's doing, but it's not as good as the 64 into 64. For 64, it is kind of over 96%. But lipstick is a bit low, but model is fooled most of the times. The question regarding this table was comment on the results. Okay, what's the effect of the patch size? Which class is easier to fool and which is more difficult? Of course, you can see by the scores that this class that is probably more difficult to fool for this case is the toaster and the lipstick. Lipstick still stands for 64 into 64. And also this. And the easiest would be then school bus and pineapple. But here it's almost kind of same, except for the lipstick. Okay, the clear trend that we would also have expected is that the larger the patch, the easier it is to fool the model. For the largest patch size of 64 to 64, we are able to fool the model on almost all images, despite the patch covers only 8% of the image. And the smallest patch actually covers 2% of the image, which is almost negligible. Still, the fooling accuracy is quite remarkable. A large variation can be, however, seen across the classes, which you saw that at least for the 32 and 30, there are variations. While school bus and parents seem to be the class that were easily predicted, toaster and lipstick seems to be much harder. This is hard to intuitively explain why. Yeah, I also don't have any answer. But yeah, nonetheless, a fooling accuracy of more than 40% is still very good for such a tiny patch. Similarly, we also show the scores of top 5. And here the scores get a bit better. I mean, as you expect as well. So here no longer I think the lipstick is also doing better. And I mean, lipstick is not doing better. The model is doing better on the lipstick. And yeah, and this course also increases. And I think it is more than 70%. We were previously with 32 into 33, it was more than 40%. So it's fools. I mean, the model is fooled more, I would say. The question is, did you observe the same pattern as top 1 accuracy? If not, what's the difference? I would say the same pattern, but the model is fooled a bit more. So we see a very similar pattern across the class and patch sizes. 64 options, around more than 99.7% on top 5. Okay, that's what I said already. And the top 5 class. Okay, and for 32, yeah, so the small patch, the smallest one is more than 70%. Okay, now what we have is, what we want to do is, like, we want to see with the same examples that we had previously, how we would visualize with different of this patch attachment, let's say. And first we see on this 32 size, the 32 into 32 pixel size. And here are the patches. So this would be something that, yeah, so we kind of, because we don't have only one space, this is one example, but we kind of have the scores over like 4 different patch attachments for this image. And you see that the model is now saying, okay, this is a goldfish because this is the class of the patch. And range is still the second best, but it's not the highest confidence anymore. Here the model is, yeah, very confident. The patch is also goldfish. The image is also goldfish. Here again, the great white shark is the second best, but goldfish is the first. And the tiger shark is, like it was previously also model, had a bit problem. I would not say that it was wrongly predicting the normal pretend model, but it has a bit other a minimal confidence for other classes. But here now it's like, yeah, it's not even present in the first 5, the tiger shark. So it's like very confident with goldfish. When we have the score, like the prediction values with using 64 into 64 patch in size, and this is the patch size of the school bus. Now for all cases, it's again says a school bus, and you can see now that the trench is not in top 5. Here goldfish is, but the confidence is very small. And here again, yeah, it's even less. And again, here is like tiger shark is nowhere. So it's a bit more, the model is, I would say, is more fooled here. So although none of the images have anything to do with an American school bus, the high confidence is often confidence of often 100% shows how powerful such attacks can be with a few lines of code, basically. Okay, and yeah, we were able to generate patches, and then we were able to now fool the model. That was it. And yeah, I think this tutorial also has a lot of things that we covered today, but I think there is also some additional stuff. So if you are interested, you can also look there. Yeah, so that was it. Yeah, feel free to ask any questions if you have. Yeah.
What are the use cases for image serial text?
Use cases of this adversarial making.
Yeah.
I mean, were you in the
Yeah.
lecture? Yeah. So the thing is, like, so we want to see, I mean, how robust are the models? Because if you want to use this model for cases, I mean, I mean, let's say the application, real life application, you want to have a surety that this model is not failing in some cases. So these are the cases we want to test the model, and if we find adversarial images, then the idea would be then now we'll take measures to like make the model even better, work on this adversarial cases as long as it takes. I mean, usually it's not 100% perfect, so it gets a bit better, I would say.
It's a small to improve robustness.
Exactly, to improve robustness. Okay, then that's it for today. And I hope you